Hello again. Our next speaker, if y'all are ready, is an electrical engineering PhD student and licensed ham radio operator. In case anyone is curious, KD8 TUO. This is a very specific thing that some of you may know. And he has over a decade of experience working with aerospace and defense contractors, specializing in hardware security, embedded systems, and high reliability electronics. His research interests include RF and microwave electronics, hardware security, and effects of radiation on microelectronics. If y'all are ready, please welcome to the Hackaday Super Conference stage, Jeremy Hong.
Thank you so much. Yes, thank you. Yes, wow, this is real freaking wild. Okay. So, yep, this is rad reverb, right? So we're going to talk about my experience in just frying silicon with gamma rays. And so, yep, first off, have to acknowledge like my advisor, Dr. Sayu Ren, and then my collaborators at Ohio State, very important people, as well as the Nuclear Regulatory Commission for the study, as well as Digilant for providing the awesome instrument last summer that I used in the study. It was a nice little box that ended up being very useful. And so, yep, about me, I finished my master's this summer, and that's the work that we're covering here. And thank you. And so, yep, this is now my first semester as a PhD student, which is crazy. I never thought I'd ever do that. But, right, like I tell a lot of people, right, if they want to pursue more in academia, like, right, if you have something that you really want to, like, a couple questions you want answered, right, that's just you got to run with that, and then that's right. Like if you have that enthusiasm, you'll find those answers, like I did here. So now, yep, I work full time also as a RF hardware engineer at 3DB Labs, which is really good to say. And yep, because of all the above, that's why my consulting with my own company is on pause. And then, yep, as Ali mentioned, I'm a ham radio operator, and this is my second talk at SuperCon. So, yep, my approach to this presentation is there's a lot of slides that everyone can review later because it is kind of a dense topic, but we're going to try to speed run this in 20 minutes. Yep, this is basically just a informal version of my thesis defense. Like, so there are a lot of those fun things I couldn't mention in front of my advisor or just my committee, right? Because right, there's lots of ups and downs with research, and so that's what I'm going to talk about here. And then, yep, here's the overview. But yeah, that's me at Ohio State's nuclear reactor facility. It's a really cool place I'll talk about. But yeah, just some background. This started all the way back in high school of just like this dream of like, oh, I want to, like someday if I get the opportunity to go to this facility, I'm gonna say yes to it, right? And it's incredible, right? Because that's what literally happened last fall. Like literally, we got a call, these folks from Ohio State called my advisor. They really needed help on trying to get these FPGAs up and running to do destructive testing. And I guess we're kind of like the subject matter experts in the area for that. And then of course they love doing collaborations. So, and the moment I heard OSU NRL, I'm like, okay, I'm gonna do that. Whatever it takes. And yeah, most of this work, which I have to shout out, is not only my prior work, which is Silicon Reverb, but also Silicon Echoes, which were specifically hardware security applications where you're using a VNA to measure chips for hardware Trojans and such. And a lot of that theory that this group in Worcester Polytechnical Institute in Massachusetts figured a lot of the really hard math out and the theory. But of course, as I'll mention here later, they used very exceptionally expensive equipment that us mere hobbyist mortals can never afford or could dream of. So let's see. Yep, and so this is basically an overview of the Ohio State Nuclear Reactor Lab. I was fortunate enough to actually see during a test the Cherenkov radiation, so I have that off my bucket list in my life. I always wanted to see it. Yeah, they have really cool, just like, right, if it's anything emitting alpha, beta, gamma, neutrons, or shout out to Arsenio Michael waves, right? Yeah, that's there. So Yep, and then here's a couple of sources that are of primary interest. Predominantly in this talk, right, cobalt-60, cesium-137 are the ones that I spent a lot of time with. Yeah, so my first introduction to this facility, which again, I never really got a formal safety briefing. They're really good at keeping me out of places, but the one thing when I was just getting water was the sign, right? No eating, drinking, chewing gum, or applying cosmetics. And of course, this is, what was this? It was January, right? It's really cold in Ohio, so I just pulled out my chapstick and then I opened it up and I was like, wait a second, I can't do this in the reactor bay. So just put it back in my pocket. So that was my first like, oh yeah, this is like really serious, right? And then of course, have to put the slide in here, right? Have to always mention the the Demon Core and all these fun numbers, right? Like there's a lot of stuff in here that could kill you, right? Like if and it's really awful. But yeah, that slide's in here, and Ohio State ranks was that like number 14 on this list, right? Yeah, it's a fun little graphic someone made on the internet. Link posted below. And then yeah, the cool thing is, right, like you'll read like all sorts of articles from this place. It's really cool. Like literally, I did my testing in that tube, right? That's where the cobalt-60 is at the bottom, and right, like Oak Ridge uses this all the time, and then like other collaborators. So, and right, why do we do this kind of testing? It's right, basically, right before you want to like in this instance with like nuclear reactors. The NRC kind of does a study every 10 years, basically, or it's like a check where they want to see if you can put like consumer-grade FPGAs that we all take for granted are really cheap, and see if they can be used in like control systems and stuff that like all the vendors and manufacturers put out. And of course, it's very good to know like the shielding design that you need to kind of approve this. And of course, I'm fortunate enough that I was at the destructive testing phase of this study, because that's, like, in my opinion, the most fun thing, right? You're just breaking stuff. And so eventually we're supposed to then go to the next phases of this study, which is like, okay, how do you prevent bad things from happening to your FPGA? And yeah, this is just like an overview of what like the typical like testing things that people do with silicon and FPGAs. The one of focus here is total ionizing dose. So this is where you're just like letting the chip bake or cook, right? Let it cook. And so like literally like, right, depending on what source you're using, it could be hours or days, right? Like so, the nice thing is, for the example, like cobalt-60, just like 2.5 hours for the particular chips, and then cesium-137, it took like almost like overnight or a day or two, basically, where we'd have to leave it there and then let it bake, because this facility is only manned during the daytime, so we can't just go back and pull it out. And yep, so the motivation, which again, this is more or less just things for my thesis, which kind of boring, but yeah, But here's the real objective and motivation, right? Do something new and novel, build something real, leverage open source hardware and software, do EE things, and of course nuclear things are cool in my opinion, right? Like it's magic rocks, right? We're literally using hot magic rocks to destroy computing magic rocks. It's like awesome, right? And then yeah, here's an overview of let's start talking about equipment, right? Vector network analyzers. So as I mentioned with that group in Massachusetts, that particular study, they used like a $250,000 VNA, and then like as it turns out, a lot of the stuff that they were looking for was within like a couple gig to, like just a couple meg to a couple gig, so you don't need really anything that exotic. And of course, that's where this guy, the Libre VNA, fits the bill for the sweet spot for at least this study, and also it's affordable, right? It's full 2-port VNA. And by the way, you could just measure things, right? Like, again, you don't have to just measure RF circuits all the time. Like, you can measure materials. In this case, I looked so hard for this paper where it's like, right, just try to figure out the dielectric constant and RCS of bees, right? You could just measure things, guys. With a VNA, they're really good at keeping track of all the RLs and Cs, right? So. That's very important in this study. And yep, here I just have a couple of slides that explain S parameters and one-port reflection, right? So again, in this study, we're measuring reflections from the chip, like we're shooting out a stimulus, recording what's back, right, and seeing like basically all the structures inside the chip. So right, like all those transistors, voltage planes, ground planes are all reflecting back. And with radiation, as I will show you guys, that changes because when you ionize things like silicon, yeah, they tend to change the intrinsic properties, so to speak, right? And yep, just another set of diagrams. And yeah, this is where we get into now the concept of the power distribution network. So once again, with the set of FPGAs, and then of course, eventually if we have the resources and time to do it, like we can make an ASIC, ideally you want to measure at the voltage input for this kind of measurement, like literally like the VDD, but in most cases, you'll have a bunch of like, right, components and things before that, so right, like a voltage regulator module, lots of bypass caps and stuff, so then now it just becomes this giant circuit. And then fortunately, right, lots of papers exist where they simplify this down to a simple R and a C, right, very, very good, very good. It's very easy to calculate that, or at least, so to speak, black box this, right, into a very simple circuit. And that is, as it turns out, is what really the key things that are changing inside the chip are the resistive and capacitive properties of the silicon. And so, yeah, these slides I just kind of skipped over, basically just explained that in like glorious detail, like, okay, yeah, when they design chips, and then of course the power network, right, you have to make these things stable so that you don't oscillate out of control, or all those crazy things that you don't want to happen in a commercial or high reliability product. And the key thing, right, this slide, which again very important to my work, is the fact that, right, when you irradiate silicon, right, you're literally changing again intrinsic properties of the silicon, like all your thresholds change, and right, that all starts to make things really bad on the chip, right? Like it's you're changing switching points, you degrade your power efficiency, like we've seen with our ring oscillator design, before it dies, right, the I/O just like starts to droop like in performance. So it's definitely interesting to see all those changes. And yep, so yep, again, black box. We're basically measuring with a VNA, R's and C's. And yep, this is a table with just generally like, these are all the things that are affected by radiation on an FPGA. And once again, this diagram, very important. Like, right, okay, we're measuring right at the voltage input, and just watching this change while it cooks. Yeah, again, bigger slide of that. And this is the actual test setup, right? So we have a power supply hooked up to a bias T that's actually powering this thing. And then this is like almost like 20 feet of cable that's between the bias T and the device under test, right? A very safe distance while it's in a tube, right, being cooked. And then, yep, so here's the cesium-137 setup, which I will say was not really particularly a fan of these tests because, right, you have to be there for a long time. And again, most of this testing is kind of like watching paint dry or grass grow, right? And it's pretty boring, but the end effects when you're processing data, it's like, oh my God, this changed so dramatically, right? Like it's the payoff is really high at the end. But this is what the test setup looks like for Cobalt 60, which by this point when we were doing more of these tests, I had a whole like instrument rack set up that I would just carry in, and then up a flight of stairs, bring that up. And yeah, so basically if I recall, it's like 15 feet that we have to take this dut down, and then right there's like lead shielding and stuff so that the gamma doesn't get out. And yep, so this is just basically very basic board, 4-layer, impedance controlled, using Saturn PCB toolkit to figure out what 50 ohms is so that we keep all that in check with the VNA. And we used a Spartan 7 FPGA. We're thinking about expanding this out to zinc and other relevant parts. Spartan 7 was a choice that was made before I was on this project, but I just kind of went with it. Yep, very important thing is, right, mentioning calibration. So the awesome thing with the Libre VNA, right, again, full 2-port VNA, was 100 kilohertz to 6 gigahertz. There's a nice official calibration kit, right, this electronic calibration kit that automates the short, open, load, and through calibration standards. That runs, I think, off like a RP 2040, again, open source, and so that was really, right? We're trying to get, either get our test setup quickly set up, and the key thing that I learned first on, or at least really early in the study, was it was really annoying to take out the individual calibration standards, right, for my other low-cost VNAs or even the Libre VNA, and of course you drop that accidentally into the pool where the test setup is. It's like, oh, whoops. We're gonna have to wait a while, or we're gonna have to do this test some other time. And so with that, again, I will say this: it's very fast to calibrate, but it's also very fast to then make mistakes. Like, right? Oh, whoops! I didn't tighten this cable enough, or whoops! I didn't. What is it? Just let it warm up, because right, this thing has to warm up to a certain temperature before it's reliable as a calibration standard, right? Like it has to. This temperature has to settle. And yep, so I have a bunch of these other boring slides that kind of explain most of my thesis, where yes, a lot of these, especially in the upper gigahertz range here from 4 to 6, you see lots of things change. And I think I hear, yep, I just kind of defer to my thesis, like, look, just go click the link, you'll love all the Smith charts and logmag plots plus tables that I've generated. The key thing to remember is if there's a difference of 3 dB or more, right? So either literally half power in this case of loss, right? Then that's a really significant change, and we see a lot of those. And the key diagrams are more or less this, where you start to see very linear changes on many different across the different frequency ranges. So that was very reassuring to see that, because again, it's like, oh, okay, it is very clear that okay, the whole chip is definitely changing. And then here's some test notes. So again, first test was just like, okay, does our test setup work? And then I used at that time a Tektronix TTR 506 VNA to at least prove out the concept before going with the Libre VNA, and then we went with that. And then, of course, we had a software failure. The thing with running tests for a very long time is, right, your risk of then your setup failing increases, right? Like especially if you're not able to remote into it. And then, yes, tests 5 through 7, which were the tests we did before the most recent 2 I did. As it turns out, the power outlets by the Cobalt 60 radiator, which are like rounded right across this concrete wall from the reactor, are very noisy. And I like to show this picture because look at that scorch mark on this outlet. It's great. And of course, there's a nice label that says use noise filtering UPS for sensitive equipment. And again, I foolishly ignored that at the time because I'm like, oh wait, the power supply rejection ratio on all of our stuff should be pretty good, right? It's like, no. This is very bad noise. And so once I fixed that with a filtered power outlet, it was fine. So our data's from our last 3 tests are great. And again, this is still very much an ongoing study. But let's see. Yep. So so the beauty of at least CMOS technology is that when it comes to these kinds of tests is it's very linear in behavior. So again, like that's why we switched from cesium-137 back to cobalt 60, because we could go through at least 2 parts a day. If not, we could squeeze in 3 if some of the staff stayed behind longer. And so that's why we were able to get lots of data eventually. At least when I wrote this paper, it was only 7 tests. But yeah, you'll see that once this part hits about 20 kilorads, minus that first test where we were just proving out the concept, yeah, all bets are kind of off. And then the failure signature of this thing is basically the thing just dies, right? And then, especially if we leave this in the cesium-137, you just see the thing just cook, and then the current leakage increases over time. And like, right, that just, yeah, that's very bad things happen. But yes, again, study, I learned a lot about issues and constraints, right? So the thing about the Libre VNA, right, despite it being an awesome open source VNA is, right, again, lower dynamic range, higher noise floor. So we had to spend quite a bit on cables, but not like thousands of dollars. Like we just had to switch to some better coax and then I had to crimp connectors because I'm trying to remember. It's one of the RG cables that was rated up to like 8 gigahertz that for some reason on Amazon didn't come pre-crimped, but that was, yeah, again, easy for me to just kind of work around. And then, and funnily enough, right, like I had found like previous papers that mentioned like, right, the temperature drift of this thing, and this was a problem that I first solved even like when I first got the Libre VNA. I just put a couple of fans that I got from my local surplus store, and that did wonders. Like, right, it's very stable, and of course they fixed this in the new version of the Libre VNA. They just attach a huge heatsink to it, and yeah. So right, of course, right now with these two tests, it's very methodically limited, right? Because it's two tests, and then, of course, I have to mention that I at least released the Magic Smoke once because I referenced the wrong pinout on the Joule scope, which we've recently added to the test setup, and that was a very sad mistake because literally smoke came out of the bias tee. I'm just glad that the VNA wasn't the victim of this problem, but that was like, oh, of course, right? It's not really right or research unless something like that happens, and so, yep, yeah. Right now we're still working on reproducing, and again we're getting really good data now. Yeah, so future work, yeah, we're doing more data. We're going to use higher radiation sources, like I'm trying to remember, like a neutron beam and other things. And of course, Arsenio is you got to use the microwaves, man, and the proton beam, right? So yeah, so yeah, we're pursuing all those things, and then we're working on an IEEE paper to publish the results of the other things that are running on the FPGA that correlate with the radiation, and yep. So, but this key, at least my thesis and my portion of the study proved out that yes, you can use a really nice, affordable VNA to track changes in a piece of silicon pretty reliably, and yeah. So, and that's never been done before. It's new and novel, like, right. And the fact that you don't have to be you have to have this test setup like down where it's very, very hot from the radioactive source. It could do it just through coax, and then you're just we're measuring the reflections. And so, yep, I have additional references, and yep, thank you very much. Yes, and here, if you want more content, here you go. Yes. Yes. Yeah, take a picture, and then